So as usual, right, for the Laplace's equation in electrostatics, heat equation in thermodynamics, and now the wave equation for mechanical waves, the implementation of the calculation of the wave, propagation of the wave, is actually really rather straightforward, just using our difference equations. You know, most of the code is setting up the parameters of the problem. In this case, taut string, the discrete space time, and not much of the code is really the actual calculation machine of using the difference equation to propagate in this case, the wave along the string. It is slightly more complicated in this case, just because we've got a special calculation for the first step, and then we've got the standard calculation, iterative calculation for the later steps, because of that issue of the initial conditions and looking back 2 steps in time, 2 intervals in time. Okay, so let me just talk about this a little bit. In this first cell, I'm basically setting up the parameters of the problem or declaring arrays that I need for the problem, and setting up the initial wave on the string. And then in the next cell, we solve the differential equation. Actually, in the next cells, we solve the differential equation. So there were a couple of parameters related to the string on which the wave is going to travel. So one was the mass per unit length of the string. That's the rho in this equation here. One was is going to be the length of the string. So that's the L in this little block here. And then the other one was the tension in the string. So that's the T here. So I'm setting up those parameters. I calculated the velocity just because I was kind of interested what the velocity is, and we should see once we propagate a wave, it better travel with that velocity. So it's a useful check. This just defines our lattice of discrete space-time. So for my string of length 1 meter, I've got a spatial lattice that is 1 centimeter steps. And for my time, I've got a time steps that are 1/10 of a millisecond. And they're just sort of appropriate things for values for solving this problem. Just like the heat equation, right? Because we've now got space and time coordinates in the heat equation and now in the wave equation, there's a kind of coefficient that relates the space evolution and the time evolution. And so I'm just, this constant C is a handy combination of the spatial lattice, the time lattice, and the velocity of the wave to plug into the difference equation. And then, if you remember the heat equation, we made 2 arrays because we had to calculate the future time, calculate the future function as a function of time from the current function. In this case, we're going to calculate the future function from the current value of the function and that 1 step earlier value of the function, the old value of the function. So now we need 3 arrays. So I've got y, which I'm initializing to 0. That's going to be always the future value of the function that I want to calculate. And then I got y1 and y2. So one of them I refer to as the current, and one of them I refer to as the previous time, because we need to calculate the future one from 2 steps back in history. These are one-dimensional arrays that are corresponding to the spatial lattice. So at each time interval, I calculate a new function that is an array corresponding to the spatial lattice. So that's just initializing to 0. And then here, I wanted to pluck the string. I don't want to pluck the string, make it like a sine wave or a cosine wave or something like that, because those are solutions you can kind of read off from an analytical solution. I wanted to pluck it in a way that you couldn't solve this problem as a numerical solution, or at least couldn't solve it very easily. As an analytical problem, you can solve it very easily. So I imagine I got a string of some length 1 meter, and I'm going to pluck it at about 20 centimeters from one end. And I'm just going to sort of lift the string up a little bit here. So what I'm going to, and hold it here. So I've got now a string that kind of, there's this steep angle down to the left-hand end over here, and then this shallow angle down to the right-hand end over here. So some sort of triangle. And then I'm going to just release it. And we're going to watch that kind of triangle wave propagate up and down the length of the string. So that's convenient because I could specify rather simply the initial condition of the entire length of the string. And so that's what I did in these lines here. So if you look at these equations, these are for y1, so the current position of the string. So these are equations for straight lines. This is an equation for a straight line. This is an equation for a straight line. They're equations for a straight line. The upper one is a straight line from sort of the end of the string at 100 centimeters or 1 meter up to this point that's 20 centimeters away, so at 80 centimeters. So it's a fairly steep straight line. And then the lower equation there is from the sort of origin up to this point here. So I've kind of described the plucking of the string through these two straight lines. Okay, so I better execute that. Just so we're happy with that, I printed out that I plotted out this function y1, the current displacement of the string at this initial condition, at this initial time, at time 0. So here's the left-hand end of the string. Here's the right-hand end of the string. This is where I stuck my finger at 80 centimeters. You see the 80 centimeters in here. And so this is my initial condition. I also printed out the speed based on the square root, the tension divided by the linear mass density. So there's 63 meters per second. So if you think this is a meter-long string, it's going to go, the length of the string, we think in some small fraction of a second. It's going to go, the wave's going to travel roughly 60 meters per second. Okay. So this cell here is just that very first step of the propagation of the wave equation that had to be treated specially, that had built into it that we released the string from rest. And then there's another second cell where I can do, iteratively in a for loop, however many steps I want to take. So the first step here, this is the difference equation, just this piece here. And so I've got this in a for loop because I have to apply that for every space coordinate along the length of the string. And if you remember that first special case difference equation, I didn't have 2y1 minus y2. I just had y1 because I'm assuming that y2 is the same as y1. And so this is that special formula. And so when I run this, this is the new wave after one time interval. It's just one time interval, so I don't know if we can see much is happening yet. But let's go down to this next step. So in this step, one time interval was just 10th of a millisecond. So there's not going to be much displacement of the wave in that time. But in this next step, we can iterate over many steps in time and start to watch the wave propagate along the length of the string. So in this cell, I basically got this counter. I got this integer here, which is how many steps in time I want to make in these 10th of a millisecond steps. So if I make 50 of them, that's going to be 5 milliseconds. And bear in mind that the scale of the speed of the wave was sort of 60 meters per second. So if I wait 50 milliseconds, I should see the wave moving down the string. I'm going to have a counter here that will accumulate the total time I'm at. So I'm just going to keep incrementing that. And now you see I've got 2 for loops. So I've got one for loop that is stepping over the time intervals, and nested within that is a second for loop that's stepping along the spatial points along the wire. And this is using the full difference equation. So this is 2y1 minus y2. And in here, I've got to enforce my boundary conditions. I've got that in here too. Okay, so in this difference equation here, I calculate the new coordinates of the wire or the cable, and then I've got to after I've done that, I've got to update a bunch of things. So once and this reminds me of why I think it was your question. Why did I do that? Like y1 comma y equals y comma y1, so reverse things. I think I did it as a reflection of what's happening here. Now we've got 3 things to update. So when we calculate the future, we've got to update. So we're calculating a new y. The old y2 will become a y1, and the old y will become y. So I think it was just a handy. So that's what I'm doing here, and I think I inherited that to the earlier calculations. So this is just updating the history. And updating the history, you've got to be a little bit more careful here. And so now I've ran 50 time steps. We've run 5, which means 5 milliseconds, and we see this triangle-shaped wave is now propagated along the length of the wire. And I could keep executing, like I can propagate it another 50 time steps. We see it further walking down the wire. And we could propagate another 50 time steps, and another 50 times. Now this kind of peak has reached this end of the wire. It's going to get reflected off the left-hand side, and now it's coming back the other way. Now, one thing you might notice is that it's starting to get more and more jagged as it walks up and down the length of the wire, the length of the string. And that is these approximation errors that are accumulating and accumulating. You have to wait a lot longer than we can wait here for it basically to dissolve away into just the noise of approximation errors. But you do see, I think, at least that is getting, less like a triangle wave propagating down and getting this other noise structure.